So they all have a 1/6 probability of rolling a 1, of rolling a 2, of rolling a 3, a 4, a 5, and a 6. So the shape of that one, when we talked about it, it was uniform because I'm on look at that first page. It's a uniform shape because uh, they are all the same. So every single one was the same. 1, 2, 3, 4, 5, and 6. When we talk about the center, it's right here between 3 and 4. So you could even say like 3.5. And then we talked about the spread. It goes all the way from 1 to 6 is the spread. When you go to the next one, sampling distribution number 1 down there said, what about when you roll a die twice? So when you roll it twice, at the bottom it says this is the average of 2 rolls. So the average, if they were both 6s, then it is possible that the average could be 6. If they were both 1s, it's possible the average could be 1, and then it could be any number in between that. So if you look, rolling 2 die is a symmetric distribution. So the shape is what we would say approximately symmetric or approximately normal because it looks like it's going the same on each side. The center would be 3.5. That's our center. Because if you think about it, rolling 2 die, the most likely thing that happens is a 7. So the average of a 7 divided by 2 is 3.5. So that's how you get that. And then the spread, again, since we're talking about the average of 2 rolls, it just goes from 6 to 1. If you look at sampling distribution number 2, what about when I roll a die 5 times? So calculate the mean, and then it says repeat this 499 more times. So it's like doing it 500 times in sampling distribution number 2. What you notice is the shape is still approximately symmetric. What you should notice is that a lot of the values have started to get closer. Okay, they're like being compressed together. They're closer to the mean. The mean is 3.5, so they're getting closer and closer and closer to that mean of 3.5. There's not as many out there beyond 5 or beyond 2 because they're all getting closer to the mean because you rolled it 5 times instead of just twice. You're getting larger. When you roll it 10 times, it gets even closer to the mean being 3.5. Notice that most of the values are between like 4.5 and 2.5, and they're not as spread out. So the more times you do something, the closer it should get to the mean or the average, and the less times you do it, obviously, the more spread out it'll be. So that is kind of goes with our scenario that says, hey, the more samples or the bigger your sample, the more accurate your results are going to be. And that's why these, as you saw those sampling distributions, they get more accurate. And that was section number 1. So that was from section 1. So we're going to go to section 2 here today. With video 2 on bias and variability, the first thing it says, can any sample statistic be used to estimate its population parameter? The answer is no. So unfortunately, it cannot. Some statistics have too much bias or error to closely estimate the parameter of interest. Okay, that's called a biased estimator. So there are basically, we want our statistic, which comes from our sample, to be able to measure the population. But sometimes our samples are biased. And so our statistics are too biased. And so it doesn't give a good estimate of the population. So if it is a biased estimator, then it does not estimate the population parameter. Okay? But if a statistic actually does closely estimate the parameter with little bias or error, then that is called an unbiased estimator. So when we're talking about polls later on today, we want to see if the poll, the goal of a poll is to measure its population parameter and as well as possible. If it does not, and if it's off by a lot, then we call that biased. It's a biased estimator. It's not good. But if it does closely match what actually happens, then we call it a very unbiased estimator. And over time, more polls get more respect from the population because they end up being unbiased over time. And so then they understand, okay, this poll is going to be unbiased as you go through. Okay, so that is the very first thing. So we want things to be unbiased. If it's biased, it doesn't give us a good estimate of the population. Okay, so let's look through the next thing. It talks about the center. So in a sampling distribution, they have the same, it should have the same mean as the population. So if the mean of the sample is, look, if you have a sample, we're talking about rolling that die, and it's saying what's the average of one roll of the die. Well, you have a 1, 2, 3, 4, 5, and 6. So the average is a 3.5. That's the real average. If we roll the die twice and we take everybody's average from 2 rolls, we get 3.46, they're saying. If you roll the die 5 times and we take the average of everybody's 5 rolls, we get 3.48. If we roll the die 10 times and we take the average of everybody's 10 rolls, we get 3.49. So what you see is happening is the bigger your sample size, 2 rolls, 5 rolls, 10 rolls, the closer you should get to the population mean. It doesn't always happen that way, but it should if it's unbiased. You should get closer and closer to the real mean the bigger and bigger your sample is as we get more accurate. Okay, so in this problem, they talked about height. So how do you know specifically if a statistic is unbiased or not? And the way that you're going to know on here is if the center is approximately the same as the population. So if a statistic is being used as a parameter estimate, it is unbiased if the center is approximately the same as the population. And I'm going to show you a couple examples here. Okay, so these are the 2 pictures you should see on your notes. These are population distribution of height, right? So the first one, the center of this one, if you actually took all those dots on there, I've saved you some time from doing that. But if you took all the dots and put them into your list and found the mean, it would be 66.07, okay? That is for the entire population. That is every single height in the entire population. So maybe this was a class of so many people, because it looks like there's 3, 5, 11, 17, 21, 22, 25. Looks like there's 28 dots in there. So maybe it's a class of 28 people. Now, a sampling distribution on the right is randomly selecting 4 of those dots and finding the mean. So every dot over there is where we randomly selected 4 people and found the mean. And we did that over and over and over and over and over. Notice the sampling distribution is not as spread out because we're taking 4 people's heights and finding their average height. And so it is closer together. It's more accurate. The mean of all of these is 65.67, which is very, very close to 66.07, right? So that's what you want. You want it to be extremely close to the population. So the conclusion that we make is it is an unbiased estimator. Now, because they're so close, if we would have gotten a mean of like 60, we would have said, oh, no, there's no way that this is unbiased. This is wrong. This cannot be a good estimate of the population. But if you know the whole population is 66.07 inches tall, and you take a whole bunch of samples and you get 65.67 inches, then you've got to feel like you did a pretty good job. Okay, you're not going to get exactly what the population is, but you should get approximately the same. So very close to what the real population is. Okay, so let's move forward to this. Talk about the range. So the range, so that's the maximum minus the minimum. So look at the range of the population. It is 75. You see the tallest person in the class was 75 inches tall. The shortest person in the class, way over here, was 54 inches tall. So the range for the entire population for all of the students is 75 minus 54. So we get 21 inches. Now in our sampling distribution, okay, this is the sampling distribution. The range actually goes from 21 to about 3. Okay, it actually goes even smaller than that. But the mean of all the ranges, so these are every range, every different range that you might get, is 10.12. So it's not basically the range shouldn't be as big when you do a sampling distribution because you're taking the average of 4 people. So you shouldn't have as spread out of a range as you do when you just have one person. So the range is a lot smaller. So the conclusion is the range is not an unbiased estimator. So the mean is an unbiased estimator usually if you have a good sample. The range is not. So we're able to get through page 1 there. That's just telling us we need to take the mean, the center of the sampling distribution. So I really like these targets. This is an awesome way to figure out if you have a good sample or not. So you want to draw in these targets, your dots. Okay. So think of your dots as like darts, right? And a really good sample is when you hit the target, right? And you're right in the target. So what you want to have is low bias. That means that it's not very biased at all. And low variability. Variability is how spread out it is. So you want it to not be very far spread out and not be very biased at all. That means you hit your target. The dots are not very spread out, and the dots are right near the center. Now, there are 3 other things that can happen. First of all, you can have high bias. That means you're way off of your target, but low variability. So you're very accurate. You're just way off of where you're supposed to be. High bias and high variability would be the worst. That means you're way off of your target, but you're also way spread out. You could have low bias and high variability. That's not extremely bad because if you look at those dots in number 2 right there, the low bias and high variability, at least they're still around the center. They're just more spread out. But in number 4, that's exactly what we want. We want low bias and low variability. We want our samples to not be very spread out and them to be centered right there in the middle of our target. Okay. Anybody got a question about that one? All right. So we move forward. The next thing that we'll look at, so that's exactly what we want, is low bias and low variability. This says match each histogram with one of the descriptions above. So if you'll look at those 4 histograms and try to match them to one of the descriptions above, if you'll take just a minute. So one goes to high bias, low variability. One goes to low bias, high variability. One goes to high bias, high variability. One goes to low bias, low variability. Look at that first histogram. We're going to look at all 4 real quick. If we take our histograms, the top one here, if you look at that top one, that one has, if you look at it, what does that have? This top one right here. A. I can look at B and I can look at C and I can see that they're centered on the mean. So they should have low bias. So I can already tell that they got low bias, B and C. So A is not centered at the mean. It's centered way over to the left. D is not centered at the mean. It's centered way over to the right. So if you look at D and A, they both have high bias. So high bias, there's low variability here because they're not very spread out. But it's not where we want it. So there's high bias in D. In A, there is high bias and high variability. So it's biased because it's over towards the side. It's not in the middle. And it's also pretty far spread out. Okay. B is what we would really like to have. It's low bias because it's right at the center, and low variability. It's not very spread out at all. C is okay, but it's not what we're looking for because it is still high variability, but it does have low bias. So we want it to be right at the population parameter. We want it to measure the population and not be very spread out. So B is the best of the 4 histograms as far as getting the entire population. Okay. Now, so in the last problem, and it says answer the last problem of the video here. This is the last problem. So it says 4 different statistics have been proposed as estimators of the population parameter. To investigate the behavior of these estimators, 500 random samples are selected from a known population, and each statistic is calculated for each sample. The true value of the population parameter, that means the whole population, the actual mean is 75. The graphs below show the distribution for each sample for the statistics. So A says which of these appear to be unbiased estimators of the population parameter, and how can you tell? And then B says which of these statistics, A or B, would be a better estimator of the population parameter, and it says to explain your choice. So I want you to try to answer those 2 questions. Which of the statistics are unbiased estimators of the population? So what does it mean to be an unbiased estimator? And then which one, A or B at the top, would be a better estimator of the population? But then you have to explain why. You can't just say B or A. You have to say why it is better. So let's try that for just a minute. Which of these statistics appear to be unbiased estimators of the population parameter? Anybody think? Is A an unbiased estimator? Is it centered around 75? That's what we're asking ourselves, if it's unbiased. A, yes. What about B? No. What about C? Yes, absolutely. It's centered around 75. It doesn't look the best, but it's unbiased. It's it has more variation, but it's still, we're talking about, is it unbiased? That means it's centered on 75. A is, C is, and D is. All 3 of those would be unbiased estimators. Now, that does not, just because it's unbiased doesn't mean, that does not mean that it doesn't have high variability. Like D has very high variability. C has higher variability on the outside. We would like for it to have more of the data on the inside like A does. So A has our, roughly or approximately symmetric. It's what we would like, but that does not mean that C and D are not unbiased estimators. So how you can tell is they are centered around the population mean, and the population mean is 75. So if it's centered around 75, it's unbiased, right? Now, B, which one, A or B, would be a better estimator of the population? A is a better estimator of population because it is centered around the true population parameter, right? So B is centered around, it would be in the 80s. There's not many right there at 75. It will be centered in the 80s. A is centered around the true population of 75. So it would be a better estimate. If we were trying to estimate the population, we would want to use A because it's centered around the true population, whereas B is centered around a number much greater than that. Let me go over this real quick, and just so you see what it is. We have two words that you really need to know and understand, and those are called parameter and statistic. So a parameter describes the entire population, and a statistic describes a sample. Okay, so there's a couple big ideas here. First of all, it's that a parameter describes an entire population. So a parameter has, if you're talking about a proportion, you're going to use the letter P. If you're talking about a parameter, if you're talking about a mean, you're going to use mu because it's talking about the whole population. For a statistic, which is just a sample, if you're using a proportion, you're going to use this little p hat because it's a prediction of our entire population. And if you're using the mean, you're going to use this little x bar. Okay? So if you see like in number 1A, those are proportions. Those are percentages. So if it's the parameter, you're going to use the letter P to say P equals that number. If it's a statistic, you're going to use P hat to equal that number. So we're looking at which one is the parameter and which one is the statistic. Which one describes the whole population parameter. Which one describes just our sample? That is the statistic. If you go to number 2, the proportion of residents who would say yes is a statistic. Describe the parameter of interest. That means what are we interested in knowing about? What population are we interested in knowing about? What is our question asking in the problem? What are we interested in? Okay, that's all that is. B, the statistic is an unbiased estimator. What does that mean? We've already talked about that. C, if you took a sample of 100 people, would the sampling distribution be different? In what way? So if you took a sample of 100, how would that change the sampling distribution? We talked about what it would do. It's not going to change the mean, but what would it do to how spread out it is? And what if you only took a sample of 50 instead of 100? How would that change how far spread out the sampling distribution is? Over here, we get an example of a sampling distribution. All these are samples, okay? These are samples from this problem. Describe the sampling distribution. That means what's the shape of it? What's the center? What's the spread? Remember how we describe things: shape, center, spread. Those are important in B. In C, it says, suppose the minimum is actually 40. Like, let's say this is actually the population is 40. Is actually where it should be, but we're centered around 45. So what would we conclude about this manufacturer's claim? And then down here it talks about describe the population distribution of all 12,000 male undergraduates. So it means what is the mean? What is the standard deviation? What does it look like? Describe the sampling distribution. How is it different from the population? So how is the sampling distribution different from the population distribution? So that's what we're going through in these. So there's 4 of these. So it's all about taking samples and trying to get